The lunar poles contain some of the most extreme physical environments in the inner solar system. Studying them presents an immediate physical problem. Passive remote sensing relies on the sun as a light source. At high planetary latitudes, sunlight arrives at severe, highly oblique angles. The angle between the light source, the surface, and the observer is called the phase angle. When the sun is the only illumination, the rugged topography of the lunar poles creates deep, permanent shadows. Because of this geometry, the interiors of these permanently shadowed regions, or PSRs, cannot be mapped by conventional photometric instruments. To measure the true intrinsic reflectance of the lunar poles, we have to remove the sun from the remote sensing equation entirely. The Lunar Orbiter Laser Altimeter, or LOLA, provides the active sensing solution to this topographic trap. Instead of relying on solar illumination, LOLA points directly downward. It fires a laser at the surface and measures the backscattered energy, creating a zero-phase angle. Because the light travels straight down and straight back at a specific wavelength of 1064 nanometers, the measurement is insensitive to local slopes. This isolates the intrinsic regolith reflectance, a metric known as normal albedo. These are global albedo maps derived from LOLA data. If we focus on the north and south polar views in the bottom panels, a clear anomaly appears. The permanently shadowed regions exhibit a higher near-infrared reflectance than the terrain that receives sunlight. We have physical proof of a brightness anomaly. To determine if this is volatile water frost, we must mathematically filter out the surrounding geological noise. We start by setting a global baseline for lunar regolith darkening, which is governed by the continuous process of space weathering. The prevailing hypothesis suggested that solar wind sputtering was the main driver of this weathering, a process that should vary intensely by planetary latitude. This density plot compares the measured normal albedo against lunar latitude to test that hypothesis. The data shows no strong latitudinal gradient. The highest density of reflectance values remains steady at 0.3 units from the equator all the way to the poles. This suggests that isotropic micrometeorite impacts, rather than the directional solar wind, dominate global weathering. This establishes how regolith behaves when exposed to space. The first confounding variable to address is mass wasting. Gravity causes mature, dark soil to slide down steep crater walls, exposing fresh rock. This fresh material is highly reflective and could be mistaken for the brightness we see in the cold traps. To measure this effect, we look at a control sample from the lunar equator, a known dry environment. The red line tracks surfaces with slopes steeper than 20 degrees. In these areas, the reflectance distribution shifts to the right by exactly 0.02 units. We can control for this by restricting our polar analysis exclusively to flat surfaces with slopes of less than 10 degrees. At these shallow angles, mass wasting is physically ineffective. Even on this flat terrain, the permanently shadowed regions remain about 0.03 units brighter than illuminated areas. Topography alone does not explain the anomaly. Next, we consider geometric shielding, or sky access. A flat plane has a wide view of space, while the bottom of a crater has a restricted sky view. It's possible the crater's shape acts as a physical shield, reducing the flux of the micrometeorites that cause darkening. We normalize the data by comparing illuminated regions and shadowed regions that have the exact same sky view. When sky access is held constant, the shadowed regions remain distinctly brighter than their illuminated counterparts. Geometric shielding is not the cause. The specific environment within the shadow must be the active physical agent. The final structural variable is regolith porosity. It is theorized that extreme cold might increase the fairy castle structure of the soil. To test this, we cross-reference the LOLA infrared data with ultraviolet data from the LAMP instrument. The ultraviolet data shows the opposite of our infrared findings. The black curve represents the cold traps. At these wavelengths, they are significantly darker than the illuminated areas. We apply Hapke single scattering equations to see if high porosity can explain this divergence. While raising the porosity from 0.4 to 0.7 accounts for the ultraviolet darkening, the calculations show it would simultaneously drop the 1064 nanometer reflectance. High porosity alone cannot be driving the infrared brightness. With mass wasting, sky view, and porosity filtered out, we are left with two possibilities. The brightness is caused by water-ice frost or a local reduction in space weathering efficiency. We use 2 Hapke models to test water ice. Linear mixing assumes discrete patches of ice, requiring 3 to 9% surface coverage to match observed brightness. Intimate mixing assumes ice grains are integrated into the soil, requiring 6 to 14% ice by weight. The alternative hypothesis is that the extreme cold traps have simply stalled the space weathering process. Darkening is caused by the production of nanophase iron during impacts. The low temperatures might inhibit the chemical or kinetic processes that create these iron spheres. To match the data without ice, these regions need a 50 to 80% reduction in submicroscopic iron compared to the rest of the Moon. LOLA's measurements at a single 1064 nanometer wavelength cannot definitively distinguish between intimate ice and a lack of space weathering. Definitive identification requires a multispectral approach on future missions. This chart shows the modeled spectral footprint of the ice concentrations we just calculated. The Hapke models predict weak absorption features at 1.5 and 2.0 micrometers, but a massive, intense absorption feature at 3.0 micrometers. Future active spectrometers must specifically search for this 3.0 micrometer band. If that specific signature is missing, the ice hypothesis fails, and the anomaly is confirmed as a localized pause in space weathering. By controlling for geologic variables and identifying these specific targets, we have isolated the evidence needed to finally confirm the presence of lunar polar water.